All right, so we're in 14.6 now. We're talking about the directional derivative and the gradient vector. So these are very important concepts, the gradient vector in particular, that are going to be of relevance to us throughout the rest of the course. The concept of the directional derivative is also important, but it's kind of what motivates the definition of the gradient vector, as we're going to see. The gradient vector is really the more important part of this section, the thing that we're going to be using the most. So let's sort of set the stage for this. Suppose we have some function z equals f of x, y. We've talked about partial derivatives and their geometric interpretations. So what is the interpretation of fx and fy, the partial derivative with respect to x and the partial derivative with respect to y, at some particular point, x naught, y naught? Well, we know that it represents the rate of change in z specifically at that point in the x or y directions. But when I say in the x direction, if we want to think of that in terms of vectors, I could also say that the partial derivative fx is the same thing as the rate of change in z in the direction of the unit vector I. Remember, I points in the positive x direction in the plane. J points in the positive y direction in the plane, and so fy of x naught, y naught represents the rate of change in z in the direction of the unit vector j. And so now if we start thinking about the rates of change in this function in the direction of some particular unit vector, the question arises, what happens if we want to look at the rate of change in our function in the direction of some arbitrary vector as opposed to just I or j, the x or y direction? And that's the first thing that we want to come up with, is a way of determining that rate of change in the direction of any particular vector, not just I or j. But in order for this derivation to work, we need to assume that the vector that we're using as our direction, the vector that's giving us the direction for our rate of change, is a unit vector. It's not going to work unless we assume it's a unit vector. But that's okay, because we can still have a unit vector pointing in whichever direction we want. So let's suppose that u is the unit vector AB. It's so its norm would be 1. Okay. All right. Now we're going to use this image here to sort of talk about the derivation that we're coming up with. So the blue surface here is the surface S, which is the graph of our function z equals f of x, y that we just mentioned. And let's suppose that f of x naught, y naught is equal to z naught, which would put the point x naught, y naught, z naught on our surface. I'm going to call that point P for reference. And let's suppose at this particular point, I'm interested in the rate of change in z in the direction of a particular unit vector u. Now, think about this for a second. The way this curve is drawn, it appears to kind of be going sort of downhill as we move into the xy plane somewhat. That's not a great way of describing it, but you can kind of see that there's differences in elevation and how the elevation changes depending on which direction I move. So for example, if I start at this point and I move in this direction, I expect my rate of change to be negative because my point is going to be going downhill as I move in this direction. That's a negative rate of change in z if you're going down. If I go the opposite direction, it looks like this surface kind of goes uphill as I move towards the z-axis. So I would expect a positive rate of change in z in that direction. If I move other directions, I get different rates of change. So it sort of gives meaning to that whole rate of change idea. It's how rapidly is our elevation changing and in what direction, up or down. But in our case, the vector u is in the plane. Notice the vector u up here is a vector with 2 components, not 3. So we're specifically talking about a unit vector in the xy plane. Okay, so that provides a direction that we want to establish our rate of change in. Now, in order to establish that rate of change, notice first of all that this unit vector u has a vertical plane that sort of passes through it, or that vector u kind of determines the direction of a particular plane that will slice through our surface S and contain the point P. So there's a unique plane that's going to cross through or intersect our surface S pass through the point P and have the direction given by u. Okay, move that up a little bit actually. So that plane, when it intersects the surface, is going to determine a curve of intersection, which we're calling C. You can see that curve right here. Okay. The rate of change, or the rate of change in Z at this particular point here, can then be interpreted as the slope of this tangent line to this curve of intersection, similar to how we interpreted slopes using partial derivatives back in 14.3. It's just now we're going in some arbitrary direction. So the goal now is to find the slope of this tangent line in that plane that's slicing through our surface. So we're going to do that in a manner that's similar to how we derive the slope of a tangent line in Calculus 1. We start with the idea of a secant line. And what I'm going to do is pick an arbitrary point Q with coordinates x, y, z on my curve C, on that curve of intersection. Okay, so now we have 2 points on that curve of intersection, and if I were to join those with a secant line, that would give me an approximation for the slope of that tangent line that we want. But what we're going to do with those 2 points first is we're going to project those points down into the xy plane. So you can see how they kind of get projected downward like this. Okay, I'm going to call the projection of P prime, and I'm going to call the projection of Q prime. And notice that their coordinates are essentially the same as the coordinates of P and Q, but because they've been projected into the xy plane, the only difference is that the z coordinates are now zeros. Okay. Now the point of doing that is that it gives me a way of sort of decomposing the vector that, well, let me back that up for a second. P prime, Q prime determines a vector down here. Okay, so you can see me kind of mentioning that vector right here. There's the arrow notation. And we have a couple of ways of determining the component form for that. So P prime, Q prime, because I have coordinates for those vectors, and if we think of those as vectors in the plane, so if we ditch the 0 and just think of them as vectors with 2 components, we know how to find the component form of a vector given its initial point and its terminal point. We subtract the components of the initial point from the components of the terminal point. So that means that the vector P prime, Q prime in component form is going to look like x minus x naught, y minus y naught. That's straightforward. But in addition to that, because we have this vector u that's determining the direction of that plane, and because these points both lie in that plane and were projected downward the way that they were, the vector P prime, Q prime is parallel to the vector u that we're using as our direction. So that means that the vector P prime, U prime is actually a scalar multiple of that unit vector u. That's a consequence of them being parallel. And because we have components for u, remember u, we said way up here, was equal to AB, that's its components. Then h times that would look like HA, HB. And so in the image here, you can see kind of this little right triangle where it shows you those components of u, HA there and HB right there. Okay? But what I just did is I found 2 different ways of representing the vector P prime, Q prime in component form. So I could equate those and specifically set their corresponding components equal together. So for example, x minus x naught should be equal to HA, which I have here, and then y minus y naught should be equal to HB, which I have here. Solving these for x and y explicitly gives me x equals x naught plus HA, y equals y naught plus HB. Okay? And what we can do now, think about what that x and that y represent. Those are the x and y coordinates of the point Q. Okay? Z is what I get from plugging x and y into my function f, because notice the point Q lies on the surface determined by our function. And so I could substitute in for x and y these new expressions, x naught plus HA and y naught plus HB, and plugging those into my function would give me z. And so that's where we're going to get this last little part right here. Again, remember the goal is to approximate the slope of this tangent line, because that's going to be what represents our rate of change. But using the secant line instead, what I want is a change in z as I go from point P to point Q over a change in the amount of distance that I traveled here. Okay, so what would that distance be, first of all? Well, the distance would be the length of the vector p prime q prime, but if you have if you find the norm of this vector, it's just h. Remember, this is a scalar h times a unit vector, so the magnitude of this vector is going to be h. That means that in my denominator here, I want to let's do it here. I want to put h, and in my numerator, I want to put the change in z to approximate that rate of change in z. Delta z is equal to z minus z naught. That's the change in z from the point P to point Q. But z, like we just said, is equal to f of x naught plus ha, y naught plus hb, based on this whole derivation that we did up here. And what is z naught? Well, again, z naught came from point P, which lies on the surface S, and so z naught is what you get when you plug x naught and y naught into our function f. So that means z naught can be written as f of x naught, y naught. Now, as you would expect, this approximation to our tangent, or the slope of our tangent line, is going to get better and better as h shrinks to 0, by the same reasoning that you use in Calculus 1. So if we apply a limit as h goes to 0 to this difference quotient here, then we get the slope of that tangent line. And we call that slope a directional derivative. Specifically, it's the directional derivative of f at x naught, y naught in the direction of the unit vector u, which has components a, b. And the notation that we use is this one. If you remember when we introduced partial derivatives, one of the notations that we saw was this capital D with a subscript. Partial derivatives with respect to x would have an x down here. Partial derivatives with respect to y will have a y down here. And what I had said back then was that we generally don't use that notation very much in this class. Directional derivatives are sort of the one exception to that rule, because now it's convenient to be able to write which unit vector we're using as a subscript down here. So capital D with a subscript of u, that unit vector that we're using as a direction, of f of x naught, y naught is equal to the limit of that difference quotient that we just discussed, assuming that limit exists. Okay, so that's going to give us the rate of change in the direction of u for this function f of x at the point x naught, y naught. Okay, now let me come back to this real quick. So just like when you learn about derivatives, just like when we learned about partial derivatives for the first time, we start with this limit definition, but then we don't really use that limit definition directly if we want to compute a derivative, or in this case, a directional derivative. We want to come up with some easier technique for computing these things. And the first theorem that we're going to look at does exactly that. So if f is a differentiable function, remember we gave a definition for differentiable back in 14.5, so the previous section. Or sorry, 14.4 is where we talked about that. If f is a differentiable function of x and y, then f will always have a directional derivative in the direction of any unit vector u, where the components are a, b. And not only that, computing the directional derivative is actually very easy. The directional derivative in the direction of u of f of x, y is just equal to the partial of f with respect to x times a, that u component, or that component of u, plus fy of xy times b, the second component here in u. Okay, now that's easy to do, but we need to show that this works. So we're going to walk through a little proof here. This is straight out of your book, and it's a interesting proof. It makes use of that chain rule that we talked about in the previous section. So first, we're going to define a function g, and it's going to be a single variable function where the variable is h. G of h is equal to f of x naught plus ha, y naught plus hb. Notice we're getting that from this guy right here in our difference quotient. Okay, so by the definition of our directional by the definition of the derivative in calculus 1, if I wanted to find g prime of 0, that's equal to the limit as h goes to 0 of g of h minus g of 0 over h. That's just straight from calculus, okay, calculus 1. But what do these functions actually represent in terms of our two-variable function f? Well, g of h is this. We defined g of h up here. G of 0 is what you get from plugging 0 in for h. And notice that's going to cause this HA term and this HB term to go to 0, giving me just x naught, y naught. So that's where this second portion comes from. Okay? But by doing that, what we ended up with was the very definition of our directional derivative in the direction of u. So our directional derivative that we're looking for is the same thing as g prime of 0 based on how we defined g up here. Okay? But let's look at this from a different perspective. We can also write g of h equals our function f of x, y, where we define x to equal x naught plus ha and y to equal y naught plus hb. Notice making those substitutions in for the x and the y here gives us what we originally defined g of h to be. Okay? And the purpose of doing that is to show that we can think of g as the result of a composition of functions here. So this expresses f as a function of two variables, x and y, but then each of the variables x and y can each be thought of as functions of a single variable, h. So that, to me, says chain rule. If I wanted to take the derivative of this function, thinking of x and y as functions of h, and I'm taking my derivative with respect to h, then by the chain rule, that derivative comes out to this down here. So differentiating both sides with respect to h, I get g prime of h equals this. And remember, that's the chain rule. Okay? But each of these we can write in a equivalent form. So partial of f with respect to x, partial of f with respect to y. We use this notation a lot, fx and fy. What is dx dh? Well, remember, up here, we showed what x looks like as a function of h. If I differentiate this with respect to h, x naught is a constant, so it goes away, and the derivative of ha would just be a. So that dx dh reduces to the constant a. Similarly, using this definition for y, dy dh becomes b. Okay, so looking at that, we can plug 0 in for h to see what g prime of 0 looks like. And the reason we would do that is because, again, up here we showed that g prime of 0 is the same thing as our directional derivative. But what would that be? Well, if we're going to plug a 0 in for h, I don't see any h's showing up here, but where they would show up is where x and y are defined as functions of h up here. Notice if I plug 0 in for h up here, x will equal x naught. And if I plug 0 in for h up here, y will equal y naught. So when h is equal to 0, the x's and y's become x naughts and y naughts, and we get this. So finally, because g prime of 0 is equal to the directional derivative that we're looking for, but it's also equal to this, I can set those two things equal to each other, and that's what my theorem is telling me I can do. So this is how we evaluate a directional derivative in the direction of u, which has components a, b. And again, it's extremely important to remember, and we'll see why in an example that's coming up, that u needs to be a unit vector. It has to be a unit vector, or else this is not going to work. A quick consequence of this theorem is what happens if we give the direction of u in terms of the angle that it makes with the positive x-axis instead of in component form. So here's what I mean by that. If u makes an angle of theta with the positive x-axis, and again, assuming that u is a unit vector, it should be pretty easy for you to see that we could write u in component form as cosine of theta, sine of theta. So this becomes the a and the b in this little formula, which means I could rewrite my directional derivative in the direction of u this way. Swap the a and the b out for a cosine of theta, sine of theta. All right? So let's see if we can do a couple of examples to get some practice with this idea. So starting with this one, we want to find the directional derivative of the function f of xy equals xy cubed minus x squared at this point, 1, 2, in the direction of the angle theta equals pi over 3. And again, we interpret that as an angle made with the positive x-axis. So let's think about what we need in order to find that directional derivative. I need the partial derivatives of my function with respect to both x and y, and I'm going to plug the point into those to get actual values for those. And then I also need the cosine and the sine of my angle. Let me find those partial derivatives first. So what is fx equal to? Well, this is a polynomial. It's pretty easy to work with. I can see that fx will equal y cubed minus 2x. What is fy equal to? Fy is also pretty easy. It's going to be 3xy squared. Okay, now let's plug the point 1, 2 into these. So I get fx of 1, 2 is equal to, this would be 2 cubed, which is 8, minus 2, so that's going to be 6. And then I also need fy of 1, 2. That's equal to 3 times 1, that's 3, times 4, that's 12. Okay? So, the directional derivative in the direction of u of f of 1, 2, I'm plugging in that point 1, 2, is going to be equal to fx of 1, 2, which is 6, times the cosine of the angle that we're using for our direction, that's pi over 3, plus fy of 1, 2, that's 12, times the sine of that angle, pi over 3. What does this work out to? 6 times 1/2 plus 12 times root 3 over 2, or if you simplify, 3 plus 6 root 3. Okay? So that would be the directional derivative in that direction at that point. Notice it's fairly straightforward. The partial derivatives here were pretty easy. Let's take a look at a different example now, where we're not given an angle. We're still being asked to find the directional derivative of a function. This one, coincidentally, is at the same point, but this time we're told in the direction of a vector v equals 3, 5. Okay, so what I'm doing is I'm using this original formula up here, where I need fx and fy at my point, and then I need the components of the unit vector that we're using for our direction. Now, before anything else, notice v here is not a unit vector. It's a vector. It gives us direction just fine, but it's not a unit vector. And if it's not a unit vector, then the formula that we just looked at is not going to work. Our derivation of that formula depended on this direction being given by a unit vector. So I need to take this vector and normalize it so that I can get a unit vector with the same direction. Okay, now if you remember how to do that, we compute the norm of this vector. The norm of this vector would be root 34. And so u, the unit vector that I want, is 3 over root 34, 5 over root 34. I'm not going through the steps of computing that magnitude because we've done so much of that you should be able to determine how I got this from this. But it's going to need to be this vector that we use for our a and our b, not this one. Okay? Now we need fx and fy. What is fx? Well, I'm taking the partial derivative of this function here, x over x squared plus y squared, with respect to x. I would need to use the quotient rule on this. I am going to, for the sake of time, jump to the answer, because this is all calculus 1 stuff, really. And if you want, you can kind of fill in the gaps there, but we should get y squared minus x squared over x squared plus y squared, quantity squared. I'm going to do the same thing with fy. Instead of using the chain rule or the quotient rule, I'm just going to go straight to an answer. We should get negative 2xy over x squared plus y squared, quantity squared. Okay? We need to plug our point 1, 2 into these partial derivatives. What is fx of 1, 2? Okay, so that would be 2 squared minus 1 squared, that's 3, over 1 squared plus 2 squared, that would be 5, and then I square that, and I get 25. So that'd be 25. Fy of 1, 2. Okay, that'd be negative 2 times 1 times 2. That's going to be negative 4. And I have the same denominator here that I did here. That would also be 25. Okay, so putting all of this together, the directional derivative, with the direction of u now, of my function f at the point 1, 2 is going to look like fx of 1, 2, which is 3/25, times the I component of my unit vector u, so 3 over root 34, like that, plus fy, which is actually a negative number, so let me write that as minus 4/25, times this guy, 5 over root 34. Okay, that's going to work out to negative 11 over 25 root 34, doing the arithmetic. So there's my directional derivative that I was looking for. Okay, that's going to be it for this first video. We'll continue on in the next.